In this video, I will talk about the operation of a bistable multivibrator. The word bi means two. That means the bistable multivibrator will have two stable states in the output. A multivibrator circuit is used to produce non-sinusoidal waveform, especially square or rectangular waveform. And a square or rectangular waveform will have two states, 0 or 1. 1 means plus VCC level. In case of this bistable multivibrator, the output will be stable both these 0 and this 1 levels. That means the output can stay indefinitely for any of these two states. Let's say at any instant the output is at logic 0. Therefore, if I don't apply any external triggering pulse, it will stay at that level for indefinite time. If I apply a single pulse, the output will have a transition from 0 to 1 level, and if I don't apply any additional triggering pulse, the output voltage will now stay at level 1 for indefinite time period. If I apply an additional triggering pulse, our output will have another transition from 1 to 0, and it will be stable in that state. That means it will give us output voltage equal to 0 volt for indefinite time. Let's say I have a bistable multivibrator here, and a bistable multivibrator will use two identical transistor Q1 and Q2. And in my circuit configuration, I will take the output across the collector and emitter terminal of the transistor Q2, and you will see that initially, before application of the triggering pulse T1, our output voltage will be equal to plus VCC, as this bistable multivibrator has two stable states. That means the output will stay at this plus VCC level forever if I don't apply any external triggering pulse. Now let's say at this instant I apply the negative triggering pulse T1 here, and our output will now have a transition from logic 1 to logic 0. And if I don't apply any external triggering pulse at this point, from this point to onwards, then the output voltage will be stable at this 0 level, and it will stay at this level forever unless we apply an additional triggering pulse. Let's say at this instant I have applied this negative pulse T2. The output voltage will have another transition from this 0 to logic 1 or plus VCC level, and the output of this bistable multivibrator will stay at this level forever unless we apply an additional triggering pulse. See, the output of the multivibrator is stable in both this logic 1 level and this logic 0 level. That's why this is known as bistable multivibrator, and the operation of a bistable multivibrator is dependent upon the switching properties of a bipolar junction transistor. Now let me discuss that. The operation of a multivibrator circuit will be totally dependent upon the switching property of a bipolar junction transistor. When the bipolar junction transistor acts as a switch, it will have two states, on state and off state. A bipolar junction transistor is said to be in on state if I supply a positive voltage of plus VCC at the collector terminal when the input voltage Vi is less than 0.7 volt. This transistor will be in off state. When the transistor is in off state, the collector and emitter terminal gets disconnected from the circuit. Therefore, this transistor will act as a open switch. Therefore, the collector current IC will be equal to 0. As the collector current becomes 0, the voltage difference between the collector and emitter terminal VCE will be equal to plus VCC. So when the transistor is in off state, I can summarize it. Our collector and emitter terminal will get opened, and the collector current IC will be equal to 0, and the collector to emitter voltage VCE will be equal to plus VCC. Now if I apply an input voltage base to emitter voltage Vi greater than 0.7 volt, our transistor will be in on state or in saturation mode. When the transistor is in on state, the collector and emitter terminal will get shorted. As the collector and emitter terminal gets shorted, therefore the voltage between the collector and emitter terminal will be equal to 0 volt, because we are taking the output we are taking this VCE across a short circuit, and the current that is flowing in the through the collector terminal will be IC saturation current. So I can summarize this property: when the transistor is in on state, our collector and emitter terminal will get shorted, and collector current will be equal to IC sat, and VCE, collector to emitter voltage, will be equal to 0 volt. So this is the circuit structure of our bistable multivibrator circuit. Here we have used two transistors, Q1 and Q2. Both of them are from same family, but although they are from same family, but they don't have similar doping profile, which I will show you in my later part of this video. The collector terminal is loaded with resistor R1, and the collector terminal of Q2 is loaded with collector load R4, and you will see that the base of the transistor Q2 is connected with the positive terminal of VBB with the resistor R6, and the negative terminal of the VBB is connected with the emitter, and you will see that the positive terminal of VBB is connected with the base of the transistor Q1 with this R5, and the negative terminal is connected with the emitter. I am applying a negative triggering pulse T1 at the base of the transistor Q1 through the capacitor C3, and another negative triggering pulse at the base of the transistor Q2 using the capacitor C4, and you will see that the collector of the transistor Q1 is connected with the base of the transistor Q2 through a parallel RC network, and the collector of the transistor Q2 is connected with the base of the transistor Q1 through a parallel RC network. The capacitor C1 and C2 are used to improve the switching characteristics, and the capacitor C1 and C2 will bypass the high frequency components of our square waveform. Therefore, in the output side we will get distortionless output voltage. Now let me describe the operation of this bistable multivibrator circuit. Here we have two transistors, Q1 and Q2, and you will see that the positive terminal of this VBB is connected with the p-type base of the transistor Q1, and the negative terminal is connected with the n-type emitter of the transistor Q1. That means this VBB is trying to drive the base to emitter junction is in forward bias, and so but this transistor will not be in on state unless we supply this plus VCC, and you will see that the positive terminal is also connected with the base of the p-type base of the transistor Q2, and the negative terminal is connected with the n-type emitter of the transistor Q2. That means this VBB is trying to drive the base to emitter junction of both this transistor Q1 and Q2 in forward bias. Therefore, if I supply this plus VCC by closing the switch S, both of these transistor Q1 and Q2 will try to drive in on state, but due to the doping difference, one of them will turn on first. Let's say this transistor Q1 is turned on before Q2. That means initially this transistor Q1 will be in on state, and this transistor Q2 will be in off state. As the transistor Q1 is in on state, that means the collector and emitter terminal will get shorted, and you will see that the voltage across this collector to ground terminal will be equal to 0 volt, because we are taking the output across a short circuit. And in case of this transistor Q2, as it is in off state, that means the collector and emitter terminal will get disconnected from our circuit. As the collector and emitter terminal gets disconnected, therefore the collector current in this circuit will be equal to 0. Therefore the voltage drop across this R4 IC2 R4 will be equal to 0. That means this applied plus VCC will be appeared across this terminal and this terminal, and you will see that our output voltage will be equal to plus VCC. if I don't apply any additional triggering pulse, this voltage, the voltage between the collector terminal of transistor 1 to the ground will stay at this 0 level forever, and the voltage between the collector and ground terminal of the transistor Q2 will stay at plus VCC level forever, and this state will never change unless we apply any external triggering pulse. And you will see that this VBB is driving the base to emitter junction of the transistor Q1 in forward bias. Therefore our transistor Q1 will be in on state. Now to override the effect of this VBB, that means now I will apply a negative voltage so that the base to emitter junction of the transistor Q will not be in forward bias. Therefore this transistor Q1 will be in off state. See, now let's say I am applying a negative triggering pulse. Negative triggering pulse, that means the pulse will have a voltage of minus Vs, and this negative voltage is obviously greater than this VBB. Therefore it will override the effect of this VBB, and it will drive the base to emitter junction of the transistor Q1 in reverse bias, because if I apply the negative pulse, the negative terminal of this pulse will be connected with the p-type base, and the positive terminal will be connected with the n-type emitter. Therefore this base to emitter junction will be in reverse bias. If the base to emitter junction of the transistor Q1 is now in reverse bias, that means the collector terminal, the transistor Q1 now will be in off state. And when the transistor Q1 is in off state, that means our collector and emitter terminal will get disconnected from this circuit. As the collector and emitter terminal gets disconnected from this circuit, our collector current IC will be equal to 0. Therefore the voltage drop across this R1 IC1 R1 will also be equal to 0 volt. That means the applied plus VCC will be appeared across the collector to emitter terminal of the transistor Q1. Now our voltage will be at plus VCC, and the operation of a multivibrator is such that when a transistor is in off state, another transistor will be in on state. Now let me discuss how this transistor goes in on state. So now our transistor Q1 will be in off state due to the application of this negative triggering pulse. Therefore the voltage difference between this point and this point will be equal to VCC, and the positive terminal of this VCC will be, and the collector terminal will be the positive terminal of this VCC, and the emitter terminal will be the negative terminal of this VCC. And you will see that this VCC will be applied to the p-type base of the transistor Q2, and you will see that the negative terminal of this VCC will be connected with the n-type emitter of the transistor Q2. That means the voltage difference between this terminal and this terminal is trying to drive the transistor Q2 in on state by keeping the base to emitter junction in forward bias. And in addition to, you will see that the positive terminal of this VBB will also be connected with the p-type base, and the negative terminal of this VBB is also connected with the n-type emitter. That means if I consider the mutual effect of our plus VCC and plus VBB, both of them are trying to drive the PN junction or the base to emitter junction of the transistor Q2 in forward bias. As we have connected plus VCC at the collector terminal of the transistor Q2, now our transistor Q2 will be in on state. When this transistor is in on state, its collector to emitter terminal will get shorted, and our output voltage now will be equal to 0 volt, as this transistor is now in on state. So after application of the first triggering pulse T1, the voltage across this collector to emitter terminal will be equal to plus VCC, and the voltage across the collector to emitter terminal will be 0 volt. If I don't apply any additional triggering pulse, the collector to emitter output voltage will remain at this level for indefinite time period, and the collector to emitter terminal in case of this transistor will remain at this level for indefinite time period as long as we supply plus VCC in this circuit. See, both of these 0 and plus VCC levels are stable in case of this multivibrator circuit. If I apply an additional triggering pulse, negative triggering pulse T2, the negative triggering pulse have a value of minus Vs for a time interval of 0 to Tp, and the value of this negative voltage is greater than this voltage VBB. That means if I apply this negative triggering pulse, it will drive the base to emitter junction of the transistor Q2 in reverse bias. Therefore, now this transistor Q2 will be in off state, and when the transistor Q2 gets in off state, I can disconnect the collector and emitter terminal across. I can disconnect the collector and emitter terminal from our given circuit, and you will see that collector current will be equal to 0. Therefore, IC2 R4 will be equal to 0. Therefore, our output voltage will now again have a transition from 0 to plus VCC, as the collector terminal of the transistor Q2 is connected with the p-type base, and the emitter terminal of the transistor, and the potential difference between these 2 points is VCC, is connected with the n-type emitter of the transistor Q1. This VCC in addition to this plus VCC in addition to plus VBB will now will drive the base to emitter junction of the transistor Q1 in forward bias. Therefore, now this transistor Q1 will be in on state, and as the transistor Q1 is in on state, I can short the collector and emitter terminal of the transistor Q1. Now our output voltage will again be at 0 volt, and it will stay at this level if we don't apply any additional triggering pulse. See, the output of the transistor, see, the output of this multivibrator circuit is stable both at 0 level and at plus VCC level, and the transition occurs if we apply any triggering pulse. If we don't apply any triggering pulse, it will stay at either 0 or plus VCC level, as the output of this multivibrator circuit can remain fixed at both this 0 and plus VCC level. That's why this is known as bistable multivibrator circuit. It has another name, that is called flip-flop. A flip-flop is a memory storage device which can store one bit at a time. And if you see that, if I represent the 0 level with logic 0 and represent the plus VCC level with logic 1, the bistable multivibrator can store the 0 or 1 bit at its output for indefinite time period. That's why I can term it as a flip-flop. There is another explanation of the word flip-flop in case of this multivibrator circuit. If I consider this output voltage, if I consider the collector to emitter voltage of the transistor Q1, at first it was at 0 level. If I apply a triggering pulse T1, the output will flip to plus VCC level. If I apply additional triggering pulse T2, our output voltage will flop to 0 volt. That's why this is called flip-flop circuit. Okay, that's it. Thank you. While discussing the operation of a multivibrator circuit, I have told you that no two identical transistors have the same doping characteristics. To show that, I have set two BC547 NPN transistor here. Let's say this is our BJT1 and this is our BJT2. We can understand the difference in doping profile by measuring the built-in potential of this transistor 1 and this transistor 2. Both of them are BC547. See, in case of this transistor 1, the base to emitter junction voltage is equal to 0.612 volt, whereas our transistor 2 base to emitter voltage junction voltage or built-in potential has 0.611 volt. This indicates that although they are from same family, they don't have similar doping profile. If I measure the collector to base voltage, because if this is an NPN transistor, it will have two PN junction. One is from base to emitter and another is from base to collector. Here our transistor 1 has shown collector to base junction voltage 0.608 volt, whereas our transistor 2 is showing collector to base junction voltage 0.607 volt. This indicates that although they are from same family, they don't have identical doping profile. Therefore, they will not act similarly when we supply a bias voltage in a multivibrator circuit, and one of them will try to trigger on ahead of other. Okay, that's it. Thank you.